Okay, hello everyone and welcome back to your YouTube channel. As you must be aware, I am recording this series of videos for my students of electromechanical conversion systems. And one very important aspect when we are designing electrical machines is the performance of the magnetic core. And one very important indicator of that is basically the active power losses at the magnetic material. And one of those losses is the hysteresis losses. So today I have this very simple numerical example about hysteresis losses and magnetic field. So today we are doing this, we are solving this very simple example, and in this very basic example, we are calculating also the magnetic flux density. So let's start without further delay reading this statement over here, okay? A test of a two-winding power transformer found that the hysteresis loss density, and look over here, this is hysteresis loss density, is 250 watts per cubic meter. Remember, when we are talking about density, hysteresis loss density, we are talking about units of watts per cubic meter for this case. And this hysteresis loss density is defined when the maximum flux density is 1 Tesla and the frequency of the signal applied is 50 Hertz. So we have a very interesting question over here. Calculate the hysteresis loss density, again watt per cubic meter, if the magnetic flux density is increased from 1 to 1.25 Tesla and the frequency is reduced over here. You can see 16.25 Hertz. Assume that the hysteresis loss density over the range to be proportional to this exponent 1.6. In other words, we are talking about the hysteresis loss density. That is the reason that we are using H in lower letter. And this is the statement equation for that. KH is basically the constant from statement coefficient. F is the frequency. Bm is basically the maximum magnetic flux density in Tesla. And the unit of all of these is basically, for this equation, watts per cubic meter. So as you must be aware, I am using MATLAB Live script. I define here the frequency for the first test with the magnetic flux density 1 Tesla. Also, you can see that the hysteresis density loss, in this case watt per cubic meter, is 250. So we have a second operating condition where the frequency is 16.25 Hertz and the magnetic flux density is 1.25. So you can see over here, I am presenting the equation number 1. The equation number 1 represents what we know as the statement equation. Over there, you can see that the units is watts per cubic meter. So from the first operating condition, we know that this is 250 watts. We know the frequency, we know the magnetic flux density, but we don't know the statement hysteresis constant, KH. So the first step solving this problem is extracting from the equation number 1 the statement hysteresis constant, KH. And you can see over here that doing so, we obtain this amazing equation number 2. And over here, you can see that the equations say that we are dividing 250 watts by the frequency that is on the first condition, 50 Hertz and 1 Tesla. And remember, the exponent is 1.6. So from there is simple to see that the KH is 5.0. Second condition can be easily calculated. We are decreasing the frequency to 60 and a quarter, and we are increasing the magnetic flux density to 1.25. So using the equation at equation number 1, we can obtain the numerical value of the hysteresis density loss, and you can see 116.11 watt per cubic meter. So yes, this is a very simple example. We are using in two different ways the same equation. We are using the first condition to obtain the statement hysteresis constant, and then we are using the equation number 1, the statement equation, to calculate the total the density hysteresis loss. So this is the end of the video. However, before I go, I would like to invite you to be part of the community. Here you can see the link for LinkedIn, also YouTube, and Twitter and Instagram. And again, thank you very much for watching this very interesting video about hysteresis losses and magnetic flux density. I hope this video and the explanation helped you. And if so, please subscribe to the channel or leave a comment. I will be extremely happy to help you. Well, this is all from this video today, and I must say now, bye now.